Welcome to this lecture on digital innovations in sports for benefits and pleasure. My name is Dan Kyllenstierna. I'm very happy to be invited to give this lecture on a topic that I really like. So before digging into the content, I will present my background a little bit and why I believe that I have some inspirations for you in this field. I'm an associate professor at the Department of Microtechnology and Nanoscience at Chalmers. My research and teaching is on electronic hardware design for wireless communication. I studied engineering physics at Chalmers a long time ago. I'm also coordinator of Chalmers Sport and Technology. In this picture, I am at the Torsby ski tunnel, and we are doing some tests on athletes in the Swedish national team. What we are testing on the picture is a smart ski handle that was developed in a project together with students, and we later formed a company based on that. At the end of this presentation, I will present the innovation journey that we have had in this company. Even longer ago, before starting at Chalmers, I have been a cyclist on highest international level. I never did the Tour de France, but I can promise you I aimed all I could to reach the limits of my potential, and I think I reached quite far. In my research, I have an interest for numbers, and I have applied that also on my sport, and that started my interest for measuring and analyzing performance. And I think I have spent almost as much time to analyze my sport performance as I have spent on research. So with this background, I think I hope I can inspire you a little bit in the field of digital innovations in sports. So what will we talk about today? First, I will try to present how I see digitalization in a wider context. Then we will look into digital innovation drivers in sport. We will see that we have two different digital innovation drivers. We have for performance data and we have for sharing data. And specifically in this presentation, we will present the two fields, but we will specifically focus on performance data acquisition. And I would like calling this making the important thing measurable rather than the measurable thing important. And to understand what is the important thing to measure, we will look into what limits human performance. That is actually the governing nature laws. We will look into human propulsion power, how we generate the power when we ski, bike, run, swim, or whatever we are trying to do. And I will end the presentation with the innovation example of the ski power meter. So what is digitalization? There is a term digitization that is often mixed up with digitalization, but indeed I would like to stress that these terms are different. Digitization is a much more narrow term that refers to the process of changing from analog to digital, that is representing an analog signal with zeros and ones. Then we have the digitalization, that is a wider term referring to all digital technology assisting in data collection process and transfer of information in a way that it can change a complete business model and provide new revenue and value producing opportunity. And then on top, we have the digital transformation, that is a system level result when more and more processes in the society have become digitalized. We can see this as a pyramid, where the digitization is the enabling layer in the bottom, Then on top, we have the digitalization that benefits from the digitization. And the final step is the digital transformation that the society is now undergoing, where more and more processes are being digitalized. After the digital transformation, some people claim that there is no way back. The society is digitalized, and we cannot go back to the old way we did it. Jason Blomberg refers on this in this article. So if we look specifically in sports, where do we see digitalization in sports? It actually affects more or less the whole sports segment. The way we practice sport, the way we interact in sport, the way we analyze performance, and the way we experience sports. And behind the digitalization, we have the digital innovations that are enablers driving the digitalization. And I think the main digital innovations enablers are measurement sensors that digitize the signal. If we don't digitize it, we don't have any data to share and interact with. So this takes us to the question, what are we doing with the data? So I show some brands here that you probably recognize. I have grouped them. To left, we see some companies that are primarily measuring for performance analysis. They are trying to create some benefit for the athlete. They will measure some things so the athlete know how he performs and he can react on it and do it better next time. On the other side, we have some brands that are from the beginning focused more on sharing the data, sharing with friends, sharing with competitors to compare. So we can call this measuring for pleasure. It's to increase the user experience. So depending on which purpose we have here, our innovation process will look different. We will focus on different things. So if we focus to measure for performance analysis, it is very important to make what is important measurable. With that, I mean we focus on what limits our performance, and we also need to measure it with high quality. Validity and reliability are major concerns, as it is in a research field. In terms of business potential, this may be originally limited, as the target group can be quite narrow. It's elite athletes and maybe some trainers working in performance analysis. So, and as validity and reliability are major concerns, we have to focus on sensors and measurements. If we, on the other hand, are measuring for sharing, then we don't work so much on sensors. We just take what is measurable and we make that important. By sharing and discussing something, it becomes important to us. So it's actually a fact that very few people care about validity and reliability as long as they get funny facts to share. And this is where I think the largest business potential lies, because we are all social creatures and most of us love sharing before thinking. It's a fact. So here, the innovation focus is much more on databases and infrastructure for sharing so that we can compare and benchmark in an effective way and have interesting things to discuss with our friends. So I see that these two fields, they work together. So if we think about the measure for performance analysis field, it develops a lot of sensors and measurement techniques that are digital enablers. And in the second step, these are actually business enabling innovations for the sharing segment. But on the other hand, it also goes the other way around. The databases and infrastructures and interaction techniques are often not effectively developed in the performance layer, simply because it takes too much resources. So those are more effectively developed in the sharing layer, and once they are developed, they create the benefit for the performance analysis, because also in this field we have interaction between coaches and athlete-athlete interaction. So if we look at performance data acquisition, we see that in research we have been measuring for a long time. This is almost 100 years ago. We started to measure the human work capacity. Then we went into the field, and there have been textbooks written about this. I think this is an early, more or less mass market product. I had exactly this bike power meter. It's not a power meter, it's a speed meter. When I was 10 years old in the 80s, cycling around my block, it was very fun to see the speed of my bike. Later we have seen heart rate monitors, digital bike computers. Then came the power meters in cycling, which is, I think, is a really nice innovation developed in the performance analysis segment. We will see later that power is what limits the human performance when it comes to propulsion. Then we have seen more products, accelerometer supported sport watches, GPS-based sport watches. And if we now look at what have happened the past 10 years, we saw that when the smartphones came, we saw the training apps. And then we got the smart watches and activity bands. And then we connected heart rate belts to the training apps. And we have IMUs in the sport watches, including also GPS and heart rate monitors. And we get much more sensors and integration between different sensors. So a lot of things are happening in both the performance analysis segment and the sharing segment. All this data is making sense in the sharing segment. But now we are focusing on the performance analysis segment, and that is, we focus on what is relevant to measure. Make the important thing measurable rather than the measurable thing important. And what is relevant to measure is what limits our performance. And we are all limited by the governing physics. We have Newton's laws. We have force, work, energy, power, and efficiency. We have thermodynamics, the energy principle. You have probably all studied this in high school, but I will present it in a quite illustrative way. So force and motion, what does it mean if we describe it in Newton's laws? Newton's first law is that a body in rest remains in rest. We have a cat, and if you have seen a cat, you realize if it is in rest, it stays in rest. It's not easy to convince it to move. And the sum of the forces is actually zero. But Newton's law also states that the body in motion preserves its motion. this is very obvious if you look at a heavy object like a train. You see it continues to move. Here I actually stopped the movie. And to change the motion of a body in rest or in constant motion, it requires an external force large enough to create an acceleration on the moving object. And we saw that this little car didn't have the mass large enough. So now we know a little bit about Newton's laws. So what can these laws tell us about the factors that limit us? One problem is if we have too low force. A body in rest remains in rest. And if we have too low force, simply no work. But then if we have enough force, we can start the work. But if there is not enough energy, we cannot finish it. So, but most people starting a marathon, they are actually finishing. They have enough energy to finish the work. So what separates the winners from the runner-ups? It is actually in how fast they finish the work. And work divided by time, that is power. We are all limited in power. Eliot Kishore, he believes that no human is limited. But I can tell you he is limited in power, even if he is the one among us that was able to produce the most power in average in a marathon. So what is power then? Power is the rate at which mechanical work is performed or energy consumed. It's a time derivative of the work. So the average power is the net work performed divided by the time it took to perform the work. And power, can also be expressed as the force times the speed. And remember that both force and speed are vectors. To illustrate this graphically, we can look at the weightlifter. We see that the bar with its weight exerts a force downwards, and the weightlifter wants to lift it, and it lifts the weight 0.5 meter here, roughly, is my assumption. So we performed a work, or the weightlifter performed work, but what was the power? Then we need to measure the time. And with some approximations, let's say he lifted 100 kilo. It's quite impressive. I wouldn't do it, but many people can do it. And he lifted 0.5 meter, and it took about 0.5 second. Then this is 981 watts. To get the feeling about what that is 1.3 horsepower. Horsepower is another unit for power. So this was one way to understand power. Another way is to look at human propulsion power. So the bike rider does his best to move the bike forward, and the nature forces are doing the best to prevent him from doing so. So which forces do we have? We have gravity, we have air resistance, and we also have friction. So this is what the bike rider has to overcome. We cannot measure the air resistance and the gravity and friction in field, but these forces are actually balanced by the force that the bike rider put into the pedals. And we can measure this power. At constant speed, the refraining forces are balanced by propulsive forces according to Newton's law. The propulsive power is a limiting factor in human propulsion. And here is where this power meter innovation comes in. It's a very nice thing that in cycling, all power goes through the pedals into the crankset, to the chain, and into the back wheel. So now we were actually able to analyze the power that the bike rider puts into the pedal. So the next question is where this power comes from. So the power actually comes from the food we eat, and we burn this food with oxygen that we breathe in, and it's an efficiency that determines how much of the chemical energy in the food that is translated to mechanical efficiency. And our heart constantly beats to pump out the oxygen to our muscles where the food energy is burnt, and that gives us mechanical utilized work in the wheel. The efficiency in this process is about 20%. So as an example, 5 liters of oxygen gives 348 watt of mechanical power. You may also express this in kilocalories per hour. That is actually another way of expressing power. So you can create a table like this, relating your mechanical power, your maximum oxygen capacity, and your kilocalories per hour. All these are different ways of expressing the power. In mechanical power, we have taken account the efficiency, and you see that 5 liters per minute, it's actually a very good value for athletes. Real elite athletes can have 6 to 7 liters per minute. An average trained randonneur rider can have like 3-4 liters per minute. So this reasoning is actually the basis for one of the fundamental physical exercise tests, the Åstrand test. So if we want to limit what measures performance, mechanical power is the key. I think it's one of the most interesting things to measure. It has been available to measure in test labs and gyms for years in many different sports. For instance, here we see an old bike ergometer. I think this is more or less from the time when P.O. Åstrand developed his test. Nowadays we have ergometers also for rowing, skiing, and more sports. But still, cycling is the only sport where field power measurements are widely available. And we see in cycling now that the elite athletes are doing less and less tests in the lab. They are using the field data for performance analysis. And I think this is the trend also in other sports. So I would say we have a huge business potential here. The lab is moving to the field. So if we can create power meters for other sports, there is a business potential. So with this said, I will move to the second part of this lecture, the innovation journey of the power meter for skiing. So until now, I have had my hat as a Chalmers researcher and coordinator of Chalmers Sport and Technology, but I here switch hat and I represent SkiSense. So what we do here, we measure something. The principle of measurements is that we measure the axial force in the ski pool with a load cell in the handle. And we measured, so you can see here, we have the skier. This represents the ski pool. And here is the handle. It's not so easy to see, but if we can measure the axial pull of the force, and then we can use an IMU to measure the angle of the pull, and we can measure the speed with a GPS. Then from the equations that you have seen, we can calculate the propulsive force from axial pull force and angle. It's a little delicate problem because both the force and the angle changes with time. So the tangential force is a trigonometric function. And then we integrate this over the pulling cycle to get the average force. And the propulsive power is simply this expression. It's the force calculated with the speed that is also time variant. So if we look at what technology we have, here is the ski handle that is actually floating on top of the pool. So it's movable with a very small glitch. On top we have a button to switch it on off, and then it communicates with a smartphone that collects the data. Inside the handle we have a low power microcontroller, we have strain gauge based load cell, we have a standard mass produced 9-axis IMU, inertial measurement unit. We have a Bluetooth low energy transmitter for connection to the smartphone. We have a battery with a capacity of 210 milliamps hours, and this is enough for 12 hours of use. And it's rain resistant. It's not water safe to the extent that you can sink it in water, but it survives rain. We have tested it for many hours in rain. And the plastics is made with low-cost injection molding using fiber-reinforced plastic. And it weighs around 70 grams, about twice as much as a normal handle. We try to reduce the weight, but there is some extra inside. To get something, you need to pay something. So what I will present now is the journey it took to validate that this is working. What you saw on the previous slide, that was more or less the idea. Then we have to validate it in several steps that it is working before we can try it on real athletes. So the purpose was to validate how smart ski handles, including IMUs and load cells, can be used for power measurements in cross-country skiing. Are they accurate enough? Are they reliable enough? And are they easy enough to work with? Is it easy to analyze the data? We interacted with athletes to get their experience. So the planning of the study, the validation is based primarily on analysis of real-time angle and force. And we measure that using so-called force plates from a company Kistler and a motion capture system from Qualisys. And the goal was to assess whether the technology has potential to measure propulsive power within an accuracy of 5%. We think that this is more or less the limit where the technology starts to become useful for elite athletes. And this study is actually published in the proceedings from the International Conference on Science in Skiing, presented in Vuokatti, Finland in 2019. So here you see the first test we did. We have a skier moving over the force plates from Kistler, and the idea is that he should put one pulling on the force plate. This is actually Johan Högstrand, one of the skiers, one of the students that worked in the course. It was actually a bachelor project developing the first prototype of this ski handle, and he will ski over this ski plate. He is, I should say, he is now CEO of SkiSense, so he's working for SkiSense now. So let's see if we play it. I don't get the... Oh. Okay, here he goes, and you see he pushed on the plate. So Johan was one of the skiers doing this. We had 3 skiers. They skied at 3 different speeds: slow, medium, maximum. They skied 10 times for each speed and totally 90 trials. So we will see some examples how it looked. So here we see the force curve when the skier applies the force and it increases. This is actually when Johan went in maximum speed. And what's interesting here is to compare the force measured with SkiSense handle in red and with Kistler force plates in blue. And we see that there is a difference at maximum force, but at lower force, they are quite comparable. So then we looked at what happened in medium speed and what happened in slow speed. In all cases, we have problem with a peak that is somewhat different. The other thing that we need to look into is that the angle is correct. And here we see the angle from the Kistler force plate. The force plates are measuring the force component in vertical and the 2 horizontal direction. From that, we can calculate the angle of the pool, and we see that it agrees quite well with what we got from the IMUs in the SkiSense handle. And then we look at how that affects the propulsion. Then we actually calculate the force with the cosine of the angle. And we see that the problem was at maximum force here, and that is good. If we would have had a problem in the later part of the pulling cycle, it would have affected more, because here the pool is directed in the direction of motion, and then it has more influence. So actually, even if we had a problem here at the peak force, it did not affect the propulsion so much. So to benchmark, we calculated the impulse, which is actually the integral over the time variant force multiplied by the time variant, the cosine of the time variant angle integrated over the pulling cycle. And we saw at maximum speed, we got an impulse error of 2.4%, in medium speed, impulse error of 5%, and at low speed, 1.1%. So as I said, 5% was our target. So we were quite happy. It seems our technology measured within 5%. So here we have the next verification is on the treadmill. We here see Johan Högstrand on the treadmill at the Center for Health and Performance Analysis at Gothenburg University. So we will see when he is skiing on the treadmill, and we will, at the same time as he is skiing, see the force and acceleration in the handles. So now he starts skiing, he's double pulling, and you see up here, and you also see the little, we can point to here again. So you see here, you see this force curve, and you see the acceleration from the IMU, and below you actually see the markers from the quality system. We had a quality system also here to verify the angle of the poles. So, from what we do here is that from the angle of the poles, and we can verify the angle that we get from the IMUs, and we can then calculate the power that ski sense measures. On top of that, we know the friction of the treadmill. We measured it with a dynamometer, and we know the slope of the treadmill, so we can calculate the mechanical power that is refraining Johan. So, and here we compare the measured propulsive power, which is the red coming from the handle, with the estimated power from friction and speed. And we see that it agrees very, very well up to about 250 watts. Here we start to see a difference. So we see at really high speed, we have a difference, and it's on the order of, actually it's a little bit more than 5% here. But up to 300 watts, we can say it's less than 5%, and 300 watts is really a lot. So it's still very promising. So by now we have tested the innovation in the lab. The next thing is to take it into the field. This is not the first field test, of course. It's me standing at the starting line of Vasaloppet, a 90-kilometer ski race, and I did it with these ski sense handles. So yeah, this was the final test. I mean, if it survives Vasaloppet, it's I think it's one of the longest ski races. So then it's good, simply. So I won the race, I got data from the race, but we already validated data in the test lab. The most interesting thing here was to compare how much did the handles degrade during the race. Did we have a difference in the pre-race calibration and the post-race calibration? And we saw that we had some deviation. It was different in the two handles. It was about 1% in the left handle and about 3% in the right handle. So it's below 5%, which is our target. So now we have tried the handles on ourselves, and we have seen it's working. It's quite accurate. It's reliable. It survived a long ski race. Then it's time to test it on elite athletes. So here we are at Torsby Ski Tunnel. And we are doing these tests on elite athletes. If you ever develop some innovation for elite athletes, I would like to give you one advice. they plan their training very seriously, and they have very little time to test new technology that may not work. If it works, they will be happy and they will be a good role model customer for you, but don't bother them with long testing sessions before you are sure that it works. So we planned the test very carefully. They ski only 50 meters here. They start from 0 speed. It's a test that takes about 10 seconds. And what we will see on the picture here now is we will see the skier skiing, and we will see the force in the pool. So you see the pool force curve, and you see the skier. That's it. And we show these curves to the trainers later that were actually very interested in our tests. So, but this is one of the most interesting parts of this innovation journey. We developed the power meter, but the first time we met the trainers and the athletes and we discussed. In cycling, everybody knows what power is. In skiing, when we did these tests a few years ago, very few people know what is power. But what they were really interested in was this force curve. So if we look here, we see how the force is applied. That is in this moment when the skier puts the pole in the ground. This is Anna Dyvik, who actually just did the Olympic sprint in Beijing. And then after applying the force, it reaches a first peak and it drops a little bit before the skier, all the muscles has time to react. And then we reach the peak force at the later stage, where the body weight of the skier is on the poles. And then the skier maintains the force. And this is one of the most important parts in the pulling cycle. Here it's important to have a high force, because here the angle of the pole is in propulsive direction. When you plant the poles in this, most of the force is counteracted by the ground. But in the later stage, here you get the propulsion. So it's very important to preserve the force in the later part of the pulling cycle. And then we come to the point where the skier lifts the poles and goes back again, and then getting ready for the next pulling cycle. And this is an important thing to remember, getting ready for the next pulling cycle. Skiing is not about doing one good pulling. It's about doing several pullings. So we look a little bit more into this pole force curve. And what we now do is that we know that what is important is to have the force in the direction of motion, the tangential force. And that is a result of the axial pole force and the angle of the poles. So if we do this trigonometric multiplication, we see that the force in the propulsion direction is the highest here, more or less at the point 3 in the previous picture. So how should we analyze this when we have several pullings? Of course, we can analyze an average pulling, but we can also look at the important factors to get high average power. So if we look here at 2 consecutive pullings, we can define some key figures. We have the pulling cycle, and the pulling cycle is actually 1 over the pulling frequency. The pulling cycle is defined as the start of one pulling to the start of the next pulling. And what more we have is the impulse from a pulling. That is actually the area beneath the tangential force. So it's the integral of the tangential force over the pulling cycle. So to get high power is about getting high impulse and high frequency. And then the power is calculated as the impulse times the frequency times the speed. And skiing faster is about increasing frequency, increasing the impulse in direction of motion, and maintaining force at high speed. Then we get high power. This is a very delicate biomechanical challenge. And the biomechanics is well analyzed by the ski trainers. They know what elements of the skiing technique they have to adapt to ski better. They know that much better than us. But what we can do is to tell them what gives high force and what gives high power. So they can use our tool as a very good feedback when they visually analyze technique. Because it's actually a fact that what looks good is not always the most effective. So what matters at the end is how much power you produce. And when we presented this to the trainers of the national team, they were really, really interested. And we have now continued this work, working with the national teams, both in cross-country skiing and biathlon. And we are also working with the long-distance ski team, Team Ramudden. So this is actually what I had to present. I would like to show a little bit where it all started, this student work. It all started at Chalmers, and you see to the left here, the first 3D printed parts of the handle. It was refined a little bit. This is more or less how far the students reached in a 15 credit point student thesis. Then we got some innovation money from Vinnova, and we refined it to a new prototype made with the CNC milling. And you see part of the electronics here. We made a new 3D printed version looking more like a normal ski pool handle. Then we went to injection molding, and this is more or less the prototype we have today. And in 2017, we took part in Chalmers Venture Cup. It's a competition for startup ideas. And we actually won everything. So here you see a happy team on the picture. So this started with a student work, and now it is a company. But it has taken 5 years. So this is, it's not a sprint, it's a marathon. We have reached some media attention. Here is Johan Högstrand. He's presenting it in Göteborgs-Posten, Borås Tidning. Another note in Göteborgs-Posten. And yeah, one more in Göteborgs-Posten when we worked with the national ski team and Team Ramudden. So to wrap up this, digitalization is defined as the business process changes due to extended use of digital tools. Digital innovation includes any tools that may leverage these new business processes. And digital innovation in sports often starts from new sensors and measurement systems developed for elite athletes. As technology matures, these innovations often become available to the mass markets and enabling new innovations for data sharing. And the innovations often start from a combined need. It starts from a need, and then it is combined with research. And after that follows prototype building, a lot of testing, and then followed by refining and more testing. And it's really a long journey. It's seldom a sprint race, rather a marathon. Yeah, that was the end of my presentation. So I thank you. If you have any question, you can contact me. I didn't put my email address here, but search on Chalmers webpage on my name and you will find it. So thank you very much and have a good day.